So we are very happy to have today Richard Thomas, who will count sheaves on Calabi-Yau fourfolds for us.
Thank you. Thanks for inviting me. So this is mainly going to be a talk actually about Fulton-McPherson intersection theory. But instead of, whereas Fulton uses vector bundles a lot, I'm going to use vector bundles with a quadratic form. And then I'm just going to go through some parts of Fulton's book, sticking square roots on Euler classes. And that will be the main part of the talk. And then I'll kind of speed up at the end and talk about the application to sheaves on Calabi-Yau fourfolds. So the main thing I'm going to do is explain this Edidin-Graham class and why I'm calling it a square root Euler class for quadratic bundles or orthogonal bundles. I'm going to explain how you localize this class to the zero locus of an isotropic section, just as you can localize in Fulton's book the Euler class of a bundle to the zero locus for section. The relevant thing here is an isotropic section. That's the type of section that respects the quadratic structure, as I'll explain. And then you can localize this Edidin-Graham class to its zero locus. And this has applications to counting sheaves on Calabi-Yau fourfolds, where you're not supposed to see the link yet. The sheaves are very different from the quadratic bundles. The quadratic bundles come from the deformation theory of sheaves, actually, but I'll explain that later. So don't keep that in mind. Don't try and relate the two. That'll be in Chow. So I'm going to try and produce I'm going to explain how to produce something called a virtual cycle on a moduli space of sheaves on a Calabi-Yau fourfold. And this is an algebraic version of a construction due to Borisov and Joyce, and they produced a real virtual cycle in ordinary homology using real derived differential geometry. And so this project was about trying to produce an algebraic version of their cycle. Okay, and then I'll explain the K-theoretic version of all this. So instead of using Chow, using K-theory. And then I'll explain the K-theoretic version of the virtual cycle. So that's something called a virtual structure sheaf. And the big advantage of having algebraic descriptions of these things and definitions of these things is that there's a torus localization formula. And that means they're actually computable, whereas BorisovJoyce class wasn't really computable. And there's a virtual Riemann-Roch theorem relating the two. Okay, but for now, forget all about that. So it's all about vector bundles over arbitrary schemes. There's no Calabi-Yaus. Everything will be complex quasi-projective, and I'm interested just in quadratic or orthogonal bundles. So what do I have? I have a Zariski locally trivial algebraic vector bundle. There's something incorrect already there, right? I said quasi-projective and holomorphic. Sorry, I'm mixing all my adjectives. Okay, an algebraic vector bundle. That's therefore Zariski locally trivial by definition. But once it has a quadratic form, the quadratic form is not Zariski locally trivial. Okay, so I have a non-degenerate algebraic quadratic form on each fiber. And by the Graham-Schmidt process, you can produce an orthonormal basis, but only étale locally, because the Graham-Schmidt process involves using square roots, as you'll remember. So what you find is that as a quadratic bundle, as an ORC bundle, you get something étale locally trivial. So you can't find Zariski locally, you can't find orthonormal bases in general. So they're the objects I'm going to be talking about. And the quadratic form obviously gives you an isomorphism from E to its dual, given by pairing with an element of E. Pairing with an element of E under the quadratic form is a linear functional, so it's a section of E dual. And so in particular, the determinant of E is isomorphic to the determinant of its dual, and so the determinant of E squared is trivial. And an orientation on E, this is different from the usual notion of an orientation, but an orientation on a quadratic bundle is a trivialization whose square is this trivialization given by the quadratic form. So it's a trivialization compatible with the quadratic form. And the way signs work is a real pain in the arse, but you have to put up with it. So due to this convention, which I'm sure you'll understand, so if I take a local basis for E, it doesn't need to be orthonormal. And then I take the dual basis for F. I want this, so the then I get this, by wedging the E's, I get a local basis for det E. Its dual basis should be the wedge of the F's in the opposite direction. That's kind of important for some pairing issues. And if you don't have this, you get other problems later on. So because of this convention, I get this horrible sign here, and you should ignore it at all times. Anyway, so an orientation, when one exists, is a Z mod 2 choice. So in other words, if O is an orientation, so is minus O, and it's a different one. It's not a C star choice. So usually you could change any trivialization of the determinant by an element of GM, but here, because we want this compatibility with the quadratic form, it's just a Z mod 2 choice. Okay, when one exists, and there's obviously some obstruction, and I'm interested in throughout this talk actually in SO bundles. So I'm assuming the obstruction vanishes and that we've chosen an orientation. So oriented orthogonal bundles correspond to 8R locally trivial SORC bundles. And then this is just motivation, this slide, but it's rather nice motivation for what this characteristic class, this square root Euler class is that I'm going to explain in a minute. So it's that basically complex, well, let me go back. This SORC is homotopy equivalent to SORR. And so underlying all these complex bundles are real bundles that they're complexifications of. Okay, so orthogonal bundles admit maximal, real, positive, definite subbundles on which the quadratic form is a real, positive, definite, real quadratic form. So it's just a metric in the real sense. Okay, so if you take the usual quadratic form on C to the R, then you just take the usual R to the R in C to the R. You just take the variables all to be real. Then that's an example of one of these, but it's not unique. And conversely, given a real bundle with a quadratic form, you get a complex bundle with a complex quadratic form. Okay, so you split the complex bundle into this real bundle on which the quadratic form is positive definite and real, and this imaginary part on which it's negative definite and real, and then the cross terms it's complex. And it reflects this homotopy equivalence. And this homotopy equivalence shows that orientations on E, in the sense of the previous slide, must be equivalent to orientations on the real bundle in the usual sense, and indeed they are under just taking real parts essentially. Okay, so if you take a local orthonormal sections and wedge them together over the reals or the complexes, you get orientations in the real or complex sense, and that's how you pass from one to the other.
Sorry, is there an easy way to see why the inclusion of real orthogonal thing is an homotopy equivalence?
Yeah, I'm sure there is, but obviously I'm not going to think of it in public.
Okay. No, I should know it, but I forgot. Maybe someone else.
Maybe Bert knows. What's the best way to say it?
I mean, let's see. It's similar to the Graham-Schmidt process, but I mean, you could also say that the quotient of the complex Lie group by the real Lie group is a symmetric space of non-compact type, and those things are contractible in Riemannian geometry. Maybe leave it at that.
Yeah, that'll do. Yeah, I think it's very simple. It's not coming to me right now. I'll think about it after and email you.
Thanks.
Okay. Okay, so for now, I'm going to work with even rank bundles. And the reason for that is that I'm interested in the underlying real bundle and its Euler class. And that's only really interesting in even rank. Obviously, in odd rank, it's either 0 or 2 torsion or something. So, so let's take even rank. So we have this underlying real bundle. It has an Euler class. So it's a characteristic class of the original complex bundle with quadratic form and orientation. And because the complex bundle is sort of E is the real bundle plus another copy of it, I times the real bundle, what you find is that the Euler class of the complex bundle is the square of the Euler class of the real bundle. And the sign is just due to the, you can imagine if I have this, where's that decomposition? Here, this decomposition here. If I take an oriented basis for this one, E1, E2, E3, and so on, and then I times E1, E2, E3, that listing those in order is not going to give the complex orientation on this guy, which is sort of E1 and then I E1, E2, then I E2. So that reordering is what introduces this sign here. So it's just to do with the orientations. Okay, but that's not interesting. So don't worry about the signs. This whole talk should, all signs should be ignored. Okay, so so we have this cohomology class, which is naturally associated to our complex quadratic oriented bundle. We call it a square root Euler class because of this relation. And we can ask, does it lift to Chow? Can we define it in algebraic geometry instead of using topology? And Bert and his student Rachel or Rebecca Field, I'm sorry, I've forgotten, showed that it does not lift to Chow with integer coefficients, but Edidin-Graham show it does lift once we invert 2. So you'll see the role of 2 later on. And it was never clear to me that they fixed the sign, but anyway, it's very important to us to fix the sign and make a universal choice of sign. So I explain how we do that in a minute. But so actually, you can drop this plus or minus. There's really a way of defining this square root of it, Euler class of E, in Chow without any sign ambiguity. Okay, and the way they did it, so you know, in homology, I was saying we take the Euler class of the underlying real bundle, half-dimensional real bundle. Obviously, in algebraic geometry, we don't want to do that. Excuse me. So what we replace those real bundles by is maximal isotropic holomorphic subbundles. Okay, so what's that mean? So a holomorphic subbundle is isotropic if the quadratic form just vanishes on it. And maximal isotropic are the ones which are as big as possible. So that's half the rank of E. So in skew geometry, like symplectic geometry, these are the Lagrangians. These are just the symmetric versions of them. So, you know, in C2, with the standard quadratic form, the real positive definite, you know, is spanned by 1, 0, and 0, 1 over the reals. And the complex maximal isotropics are spanned over the complex numbers by either this one or this one. So there's 2 separate. Don't take the span of both of them. That will give you back C2. Take either the span of this guy over C or the span of this guy over C, and that gives you the 2 different isotropics inside C2, corresponding to the 2 points in the quadric in P1. Okay, so I think I just said that. So we have these 2. We have this maximal positive definite real subspace here. So that's 2 real dimensions. And we have this 1 complex dimensional, so 2 real dimensional maximal isotropic given by this one. And there's another one here. But notice that either of them is isomorphic to this maximal positive real, positive definite real subbundle that we used in the construction of our square root Euler class. So that'll be useful later. Okay, so our maximal isotropic sits inside E. The quotient is its dual. That's because that's what the maximal condition gives you. Okay, so pairing with an element of lambda under the quadratic form annihilates lambda. That's the definition of isotropic. So it descends to E mod lambda. So we get a map from E mod lambda to lambda dual. That's true of any isotropic. And then the maximal isotropic condition is that that should be an isomorphism. So this is more familiar in the Lagrangian case. We're taking conormals of Lagrangians. Okay, and so what you recover is from this, you see that again, the Euler class of the complex bundle is the square of the Euler class of some half-dimensional subbundle. So this looks very much like the real story from before. And indeed, you should notice that the composition from the maximal isotropic into E and then projecting to one summand of that real decomposition is an isomorphism. Okay, I don't need to see that. And then there's an issue of orientation. So lambda has an orientation, a real, in the ordinary real sense. It already has an orientation because it's a complex bundle. So using the complex structure, this has a natural orientation. This has an orientation inherited from the weird orientation on E that we discussed before. And so one can ask is this composition, is it compatible with the orientations? Does it take the orientation on lambda to the one on ER? And it doesn't necessarily. And that's to do with the fact that, you know, imagine that E split here and it was just lambda plus lambda dual with its obvious pairing between lambda and lambda dual being the quadratic form. Then you could take as your maximal isotropic either lambda or lambda dual. And one of them would be oriented with respect to this, and one of them might not be. And that's good. That's where this sign is coming from. Suppose I wanted to take as the square root Euler class, the Euler class of this one, or the Euler class of this one. It's not clear which I should take, and they differ by a sign. So what I'm going to take is the one whose orientation matches up with the orientation on this real guy here. So that's what we're saying next.
Sorry, when you say orientation on lambda, what do you mean?
Well, just because it's a complex bundle, I'm talking about orientation in the real sense. You may be so algebraic or geometric by now that you don't remember what an orientation is in the real sense, right? I always forget, but it just means what does it mean? It means an element of its top exterior, a trivialization of its top exterior power over the real numbers.
Okay.
But it always has one of those because it's complex, just like any complex manifold is real oriented. So, you know, by picking a complex basis, E1, E2, and so on, the real orientation will be E1 wedge I times E1, wedge E2, wedge I times E2. So if you think of those as being different vectors in the real exterior power, even though they're linearly dependent in the complex exterior power. Yeah, it's one of those things that algebraic geometers we can never get our heads around because we're so used to working over the complex numbers.
Okay, thank you.
Anyway, because it's complex.
Can I ask more on that point?
Orientation. Sorry.
Can I ask more on that point?
Yeah.
So for lambda's orientation is in the sense that you have a basis for its top exterior power as a real exterior power.
Yeah.
Whereas lambda star is a square root of the determinant, right? Is that's like what you're saying? What lambda star is? I mean, the orientation on lambda star comes from the fact that E has a square root of the determinant, and therefore lambda star has the same property. Is that right? Does that mean
no, sorry, no, that would be no. Let me see. So I think I've got ahead of myself and I've confused everyone. So what do I want to say here? And it's because I'm trying to relate everything to the real numbers to motivate it. And I can do without the real numbers, and I can do without all these real subbundles, and just make definitions in complex algebraic geometry, and everything will work fine. So the real stuff is just for motivation. So you don't have to follow it. You can ignore it. But what I had some slides ago, let me see. No. What's the quick way of going forwards? No idea. Okay, we had this strange notion of orientation. So it was a trivialization of the determinant that was somehow compatible with the quadratic form with this star here.
Yeah.
And then there was a way of passing to the ordinary real notion of orientation on the underlying sub-real bundle. And those two are equivalent. So an orientation in this complex sense is equivalent to a real orientation on E sub R, on the real part of E. And then what that has to do with lambda, I have not said yet. And it's important that I haven't said it, and I'm about to say it. So you shouldn't think of the orientation on E as being anything to do with orientations on lambda yet.
Okay, thank you.
But lambda does have an orientation in the real sense just because it's a complex bundle. That's the only thing that you should remember at the moment. And then you could ask, when is that orientation in the real sense isomorphic to the orientation on this guy? And that's coming on the next slide. So let me do that now. Okay, so maybe the...
Sorry, I still have a question about the previous slide.
Yeah.
Does E to lambda dual come from Q? Why is it called Q?
Q was the quadratic form.
Yeah.
So what you do is you take an element of E, a section of E, a local section of E here, and you pair under Q, you pair it. So how does it give you an element of lambda dual? So I want to give, given E, I want to give a linear functional on lambda, right? So I want to say, given an L in lambda and an E in E, I should be able to produce a complex number. And it's just the pairing under Q of E and L. Does that make sense? So,
yes.
So this, I should have brought my electric pen and I haven't, sorry. So this map here takes E to Q of E comma blank. That's the linear functional. Pairing with the E under Q. That's what the linear functional is.
Okay, so I see that it goes from E to E dual. And since lambda is a sub of E, then lambda dual is a quotient of E dual. So we compose with the quotient, right?
Yeah, if you want to say it that way, yeah.
Okay.
Or you just restrict it, you know, that linear functional, Q, E, comma, blank, restrict it to lambda. Yeah, that's what you said. And that map annihilates lambda because when you pair lambda with itself, you always get 0. That's the isotropic condition. So that's why you get this exact sequence. Okay. Okay, so when E admits one of these maximal isotropics, which is not always, I should say, most E's don't. In particular, if it admits a maximal isotropic, it turns out it's Zariski locally trivial. So most E's don't admit one of these, but when they do, then there's an obvious choice of a definition of this square root Euler class in Chow, and it's up to sign. It's the Euler class of the maximal isotropic. Okay, and Edidin-Graham show this works up to this choice of sign. They show that it's independent of choice and so forth, and that it behaves nicely. Okay, now I want to fix this sign. So this is the orientation issue. So the way we fix the sign is the following. We say, because of this exact sequence that we were just talking about, this one here, the determinant of E is naturally the determinant of lambda tends to the determinant of lambda dual. Okay, and therefore it's naturally trivial. So the maximal isotropic gave us a trivialization of the determinant of E. This is different from remember the quadratic form only gave us a trivialization of the square of the determinant of E. But the maximal isotropic gives us a trivialization of the determinant of E. It's not an orientation until you multiply by some I to the n or minus I to the n because of the way all those numbers work out in all our conventions. But again, you should consider I to the n to be a sign and ignore it. Okay, so what you then do is you say that lambda is a positive maximal isotropic or a negative maximal isotropic depending on whether it matches with your orientation, in the sense that your orientation should either be, up to multiplication by I to the n, this trivialization or minus this trivialization. Okay, so this is the actual definition. All right, so we define the sign of lambda to be the image of the orientation under this trivialization. And so what we find is that these maximal isotropics split into two connected components. That's even true in linear algebra. The maximal isotropics of a quadratic vector space split into two components, and one we're calling positive and one we're calling negative. And what it amounts to is, back here, whether or not this composition here preserves real orientations. Okay, so there we go. That's that statement there. But as usual, we can do it all within algebraic geometry if we want. So this is the definition of the sign. I associate a plus or minus 1 to each maximal isotropic. I call it positive or negative according to this definition. It just happens that it has this interpretation in real geometry. Okay, and then I can fix the sign of this square root Euler class by using that sign. Okay, so if my lambda is positive, I just take its Euler class, and if it's negative, I take minus its Euler class. And that fixes this ambiguity up here in the example of E being lambda plus lambda dual, and I'm not sure which maximal isotropic to take. The signs now cancel out, and it doesn't matter. I get the same answer either way. So this is the square root Euler class when E admits a maximal isotropic. Any questions about that? Okay, so we've defined some kind of Chow class. It's not clear we've defined a characteristic class because we've got to worry about existence of maximal isotropics and independence of them, but we come to that in a second. Okay, so in general, lambda doesn't exist, but Edidin-Graham passed this sort of tautological bundle where it does exist. So there's the usual topology thing, a bit like the splitting principle. You just pass to the cover where lambda, the cover of all maximal isotropics. So here's one way of doing it. You say each point of y, what's this bundle I take over it? What's the fiber? It's just the Grassmannian, orthogonal Grassmannian of maximal isotropics. And then on this bundle, by tautology, there is a maximal isotropic in the pullback of E. So up there, we have tautologically a maximal isotropic. And then Edidin and Graham show that its Euler class descends. Okay, and the reason it descends is that they don't actually use this cover. They use some kind of isotropic flag bundle, which is some iterated quadric bundle. And using that is very easy for them to produce by wedging hyperplane classes for each of these quadrics. And they produce a distinguished class which has degree a power of 2 over the base. So what you should think of is that Poincare dual to this class is a 2 to the n cover of y. So in other words, if I cut down by this class, then this bundle here, instead of being a bundle, becomes just a finite cover. And it's got degree 2 to the n minus 1. So that means that now I can define my Euler class downstairs by just pushing down and dividing by that degree.
Okay, why couldn't you just push down without this h?
Because I wouldn't get something of the right degree. I mean, pushing down would change degree by the dimension of the fibers.
Oh.
In general, it gives 0. So yeah, so I really, I really want to replace this bundle here by a finite cover, and then I know what to do.
Okay.
And so the fact that this finite cover, the degree of this cover is a power of 2, is, and that 2 comes from, quadratic forms being, it always comes down to the fact that the quadric in P1 has degree 2. That's the 2. And that's why I have to invert 2 in coefficients. That's why Edidin-Graham invert 2 in their coefficients, because we want to divide by this 2 to the n minus 1. Any questions? Okay, so this guy now is.
I think I have a question.
Yeah, of course. Sorry, I went too fast. Yeah.
I'm sorry. Yeah, so like on the previous slide, this class H, is it like the restriction of the Schubert cycle that corresponds to a ladder to the orthogonal Grassmannian?
Which corresponds to what, did you say?
So for like Grassmannian K to K, I have this ladder K minus 1, K minus 2, etc. to 1, like a Young diagram that looks like a ladder. And if I restrict it to from the Grassmannian to orthogonal Grassmannian, I get like this number of points. I'm just not sure if it is 2 to the n minus 1 or 2 to the n. So is it like this? Like
that sounds correct. Yeah, I would. I'm not entirely sure about your notation and what ladder means and so on, but yeah, that sounds correct. So there's a way of doing it using flags of isotropic bundles, of isotropic subbundles, and at each stage of passing up the flag, you're passing to a quadric bundle in a projective bundle. That's just the isotropic condition. And at each time you're just taking the hyperplane class. So I think that sounds an awful lot like what you were saying. Yeah, so the answer is probably yes. Okay, and this class now has all the properties you'd like. Okay, so in particular, it doesn't just push down, it also, if you pulled it back, it is the Euler class of the tautological maximal isotropic. If you already had a maximal isotropic, it agrees with the previous definition. So you don't, if you already had a maximal isotropic, you can use that to define your Edidin-Graham class, or you can go up to the cover and use the tautological one. It doesn't matter, you'll get the same answer. Okay, there's a Whitney sum formula. It's equal to the class in real cohomology that I discussed before as motivation. Okay, so sorry. So yeah, it has all the properties you like. Okay, so that's the end of that. So is everyone happy with this square root Euler class? So it's just a nice Chow class that gives you the Euler class of real bundles. So it gives you the one of the generators, the important generator in the cohomology of the classifying space of SO. This is a lift of it to Chow once you invert 2. Okay, and now what we'd like to do is, just as ordinary Euler classes can be localized to zeros of sections, here we want to localize to zeros of isotropic sections. So that's a section whose pairing with itself is 0 under the quadratic form. This bit gets a bit technical, so I just summarize it here. And then if I lose you, then it doesn't matter so much. This is the result. It's that if I start with some scheme Y with an SO bundle on it. It has this square root Euler class. So that's some kind of operator from Chow of Y to Chow of Y shifted in degree. And I'm going to construct a localized operator which lands up in Chow of Z, where Z is the 0 locus, 0 scheme of S. And then under push forward to Y, this diagram commutes. Okay. So as usual, we use these coefficients where we invert 2. And that allows us to, by working upstairs and so on, assume that we have a maximal isotropic. Okay, so I'll just do that from now on. I assume I have a maximal isotropic. And I'm really only going to construct this class on the fundamental class of Y, without loss of generality. That's all you need to do. Okay, so how are we going to construct this guy? So remember, I have a section of E now. And what I cannot do, unfortunately, is assume it lands up in lambda or lambda dual. If I could, I would just up to sign take the localized Euler class of lambda or lambda dual, and I'd be done. And if my isotropic section does lie in lambda, let's say, then that localized Euler class of lambda will be the same as the class I'm going to construct now. But in general, not even locally can you do that. There are isotropic sections which certainly do not exist, do not live in an isotropic subbundle, even locally. Okay, now since the square root Euler class is the Euler class of lambda, which up to sign is the Euler class of lambda dual, what I'm going to do is take my section of E and first of all think of it as a section of lambda dual by projecting it. So I'm losing a lot of information, but I'll come back to that and use that information in a minute. So the first thing I do is I project to give me a section of lambda dual, and I'm going to localize to the zeros of that in the usual Fulton-McPherson way. So I remind you how that goes. We have lambda dual, we have a section, we take its graph, and we want to intersect it with the zero section. And how do Fulton-McPherson do that? What they do is they kind of linearize this graph around the zero section by deforming it to its normal cone. Okay, so this is the picture. Here's my graph inside lambda dual, and I just make it vertical. So I scale S dual by multiplying it by t, and I send t to infinity, and I take the limit in the Hilbert scheme sense, and I get this vertical thing. So this is the normal cone. So it's C star invariant. And the advantage of this is it lies not just in lambda dual, but it actually now lies in the restriction of lambda dual to Z dual. So it's now localized to Z dual, the zeros of S dual. Okay, and now instead of intersecting in lambda dual with the zero section, I can intersect in lambda dual restricted to Z dual. So I can intersect inside these red regions here.
Sorry, where is the dual on your picture?
It's the red, it's here, this guy. It's the red blobs.
Oh, okay.
Is that okay?
Yeah.
So I can now, instead of intersecting in the whole of lambda dual, I can intersect just in the lambda dual restricted to Z dual, so the sort of the red pieces. So I can intersect the cone instead of the graph with the zero section, and that's my localized Euler class. So that now is in Z dual, or in Chow Z dual. So that's good. We've managed to, we're not in Y anymore. We've managed to localize down to Z dual, the zeros of S dual, but that's already too big. I want to go further to the zeros of S.
Can I ask a question?
Yeah, of course.
So like this deformation to the normal cone is replacing like one cycle with another cycle, which is algebraically equivalent.
Yeah,
right?
that's right. They're rationally equivalent. Yeah.
Oh, rational. Thank you.
Yeah, so that's my rational equivalence. T lies in P1. Okay. Does it? Well, T runs from 1. Yeah, that's right. So if you take T equals 1, you get this graph. And if you take T equals infinity, you get this vertical thing. Okay, so we've ended up getting to, right, so I'm intersecting this cone, this red cone here with the zero section of lambda dual in Z dual, restricted to Z dual, okay? And the way you do that is by this Giesing map, which is just the inverse of the Thom isomorphism. All right, so Chow of Z dual by pullback is the same as Chow in higher degree of this vector bundle over Z dual. And I'm just taking the inverse, and that's intersection with the zero section. Okay, so that's given me a class in Chow of Z dual, in Chow of the zeros of S dual, which is smaller than Y, so that's good. I've localized it partially, but not enough. I want to localize back all the way to the zeros of S. And of course, by construction, the push forward of my class is the square root Euler class, because it's the Euler class of lambda dual. So that's good. So we would like to localize further. So we want to use the other half of the section. I only used its projection to lambda dual so far. But now that I've localized to Z dual, something nice happens. My section, my original section, by definition of Z dual, S dual vanishes on Z dual. So my section now, its projection to lambda dual vanishes once I restrict to Z dual. So my section actually lies in the kernel, it lies in lambda. So let me just go back to that exact sequence, okay? I've managed to localize to the zeros of this S dual here. So on that locus called Z dual, S dual vanishes, so my section here goes to 0 here, so actually it lies in lambda, okay? So I now have, on Z dual, I now have a section of lambda, not lambda dual anymore, and I'm going to try and use that to localize further. So I have this section of lambda here. Okay, so this section defines something called a cosection of my original bundle. Do you remember? Remember, I intersected my cone inside lambda dual restricted to Z dual with the 0 section. Well, that bundle has a map. It has not a section. I don't have a section of it. I have a section of its dual. So I have a map from it to O. So instead of a section, a map from O to it, I have the dual of that because I have a section of lambda. So I have a map from it to O, okay? So that's called a cosection. And the isotropic condition, which notice I have not used yet, that becomes the fact that this cone lies in the kernel of this map here, of this function. If you think of this S tilde as a function on the total space of lambda dual, the cone lies in its kernel. That's just given by taking the limit of the QSS equals 0 condition on all those graphs and taking the limit as t goes to infinity. This is the condition you get. So this is where the geometry enters. Okay, so what this says is that where this function on the total space of lambda dual is non-zero, there's a trivial normal direction to this cone, because this cone lies in the codimension 1 part of lambda dual, this kernel of S tilde. So you can sort of locally, you can think of lambda dual as splitting into 2 pieces, the bit that contains the cone, and then the bit on which S tilde is non-zero. So there's a non-trivial normal direction to this cone, and so the intersection here can be made to be 0. So there's a direction that you haven't perturbed the cone. There's an additional direction, the direction in which this S tilde becomes non-zero, in which you could perturb this cone if you were doing homotopy theory, and to make it avoid the 0 section. So there shouldn't be any intersection with the 0 section here. And indeed, the intersection can be made 0 here. And Keem and Lee do this. So they say, instead of perturbing by a section of a bundle, which we know how to do, we can also perturb by something called a cosection, which is what we've got here. And they define a way to do that. So they define something called a localized intersection. So in this case, I'm localizing the 0 section with the cone. Oh, I've missed something. I beg your pardon. That should say this localized Giesing map, and then I'm missing cone there because I want to apply it to the cone. And they give this way of constructing this localized intersection, which has been localized to the zeros of the cosection. And what are the zeros of the cosection? They're precisely that Z that I started with.
Sorry, so Z was living inside the dual, or?
Yeah, Z lies in Z dual because just tautologically,
okay.
Z was the zeros of S, whereas Z dual was the zeros of the projection of S, which contain less information. So it is easier for S dual to vanish than it is for S to vanish.
I see. So you intersect and then you intersect again.
Yeah, that's right. Well, I mean, one way of saying it is I deform so that I can rewrite the intersection in this way, and then I localize this intersection. So I localize and then I localize again. Maybe we say it that way. Okay, and unfortunately, you know, this Keem-Lee thing is really nice, but I don't have time to explain it. Basically, you just blow up so that you ensure that where this S tilde vanishes is a divisor, and then it becomes extremely simple. It becomes obvious what you should do there. Basically, that way on the blow up, you manage to split this vector bundle here into two pieces. One is the kernel, and one is a line bundle given by O of the divisor where this section vanishes, or minus the divisor or something. And everything lies in the kernel. So you know how to do the intersection there. You do the usual Giesing map there. And then you have this other piece, which is the line bundle O of the exceptional divisor. So now all you do is you just intersect with the exceptional divisor, or minus the intersection, minus the exceptional divisor, because that is the first Chern class of O of the exceptional divisor. And then when you push back down, so now you've managed to localize everything to the exceptional divisor. Now when you push that back down, that means you've localized everything to Z. Anyway, it's very simple. So there is such a construction, and so that gives us our localized square root Euler class. So that's one of the things in Fulton that we've managed to square root. Okay, so then maybe I just speed up a bit now. So similarly, we can square root the Giesing map as well as the Euler class, because essentially they're the same thing, right? It's like Poincare duality is essentially the same thing as Thom isomorphism, locally at least. So we can always also square root the Giesing map, but only on cycles inside a quadratic bundle, which are themselves isotropic. You always need this geometric condition. You can't do it on any old cone in there or any old cycle in there. And then again, it's some tautological thing using what we've already done before. So because that cone is inside the bundle, oh, sorry. And I'm just saying here that this square root Giesing map is very familiar to you. If the cone lives in a maximal isotropic, then it's just the usual Giesing map for that maximal isotropic. Okay. And so what's the construction? It's sort of tautological. On that cone, you pull back the bundle to it. And on that cone, you have a section of this tautological bundle. Sorry, you have a tautological section of this pullback bundle because the cone lies inside E. So there's a section of the pullback of E. Okay. And the fact that the cone is isotropic means that this tautological section, when restricted to this cone, is isotropic. And so what you can do is you can localize, you can take the square root Euler class that we took before of this pullback bundle and localize to the zeros of this tautological section, but that is just the original Y, the zero, the support of the cone, the zero section of the cone. Okay, and I'm not expecting you to absorb this in finite time. I can send people my slides if they want to. But anyway, you can imagine this is very similar to localizing an Euler class. The Giesing map is very similar. And so what we find is everything we need from Fulton, we can square root essentially. And again, it has good properties. All right, so that in some sense is the end of the talk about square root of Fulton. Any questions? And now I'm just going to speed up a little bit and tell you a little bit about virtual cycles. So you have to take more of this on trust. Okay, so I'm interested in Calabi-Yau manifolds, so that just means that the canonical bundle is trivial. And I'm interested in fixing a Chern character and taking moduli of sheaves of that Chern character. Okay, and I don't want to deal with any strictly semi-stable sheaves because then I have to do art in stacks and so on. So I'm going to assume that stability and semi-stability are the same for this particular Chern character. So that's like rank and degree coprime on a curve or something like that. Okay, so you can arrange that. And so I take this moduli space, and because there's no strictly semi-stables, this is already a nice projective moduli space of stable sheaves. And I want to construct a virtual cycle on it so I can do enumerative geometry and I can calculate numbers and I can talk about counting sheaves or counting sheaves, satisfying some incidence conditions and so on. But for that, I need some kind of fundamental class on this moduli space. And because this moduli space is singular of the wrong dimension, it's not the obvious fundamental class. So I need to construct something called a virtual class. And so very briefly, I'm going to remind you, in the way that mathematicians use the word reminder, what happens when you're on a Calabi-Yau threefold, and then I'll tell you how we change things on a Calabi-Yau fourfold. Okay, so this is the so-called classical theory from 25 years ago on a Calabi-Yau threefold. What you find is you do some deformation theory to look at the local structure of this moduli space. So you pick a sheaf on your Calabi-Yau threefold. Its deformations are governed by x to 1. Its automorphisms are governed by Hom, but they're just sort of constant. Because I've got stable sheaves here, they're all simple. They all just have scalar automorphisms. So you can essentially ignore this, or you can pass to trace-free Homs and then they vanish. So you can ignore that piece. Deformations are governed by x1. Obstructions are governed by x2, which by Serre duality is the dual of x to 1. Higher obstructions are governed by x3, and there's nothing higher. And again, you can ignore these. So because we have obstructions, that's what tells you that the moduli space can be singular of the wrong dimension. So the fancy way of saying this, since Berem-Fantecchi, is that there's an obstruction theory. So this is a complex of bundles on the moduli space whose fibers compute or have cohomology x1 and x2. Okay, and this is two-term. So this says that it can be written as a genuine complex of bundles such that when you restrict those bundles to F, the kernel or the zeroth cohomology is x1 and the co-kernel is x2. Okay, that's what I say there. So the H0, the kernel of this complex of bundles over moduli space is the tangent sheaf to the moduli space, and the co-kernel is its dual. That's this duality here. All right, and whenever you have a two-term obstruction theory, you get a virtual cycle. And why is that? How should you think about this? You should think about it in the following way. So what it says is that locally, the existence of this two-term obstruction theory says that locally, M is the zero locus of a section of a bundle over a smooth ambient space. So it looks like this. You have locally, your moduli space sits in a smooth ambient space, and you have a section of a bundle. Here it turns out to be the cotangent bundle. And the zeros of that section are your moduli space. And the relationship to this obstruction theory is that this obstruction theory is just the derivative at the zero locus, so on M, of this nonlinear picture here. So it's the linearization of this nonlinear picture. So if you take the derivative of this picture here, you get this. And this is what your obstruction theory looks like. So you don't have this picture globally. If you did, you would know what to do. You can see this has something to do with Euler classes, in this case, the Euler class of this cotangent bundle. And what you would do in general is take the Fulton-McPherson localization of the Euler class of this by this section, and therefore get a class in M. Okay, and you can't do that because this picture is not global, only its linearization is global, and that's given by the obstruction theory. But so you can't glue these pictures globally, but you should think that that's what's going on. That's what my moduli problem looks like. And the reason M is singular of two higher dimension is because S is not transverse to the zero section. And what I should do is try and perturb S to make it transverse to the zero section. And then that will be my correct M, my correct virtual cycle. And we're just doing a Fulton-McPherson version of that. Okay, so you can't glue, but you can't glue these pictures locally. So you can't do that, but globally, sorry. But you can glue the normal cones. So you can take the limits of these graphs, make them vertical so that they don't sit in the ambient space, but they actually sit over M. So you can localize everything to M. That's just this localized Euler class that we discussed before. And then this limit, this cone, sits in this bundle over M, which is this E1 in the obstruction theory. Okay, and then that is enough to define the virtual cycle. So now you can define the virtual cycle to be the intersection of this cone. Instead of the graph of S, you use the cone with the zero section of this bundle. And that gives you a cycle in M, and it's the correct thing. And if you were able to perturb your section so it was transverse, then you would get a cycle homological to this one. So this is the correct thing. It has nice properties. So that's how virtual cycles work, but they crucially depend on having this two-term obstruction theory. So they depend on having deformations, obstructions, and no higher obstructions or ignorable higher obstructions. All right. So that's how virtual cycles used to work. Now we want to pass to Calabi-Yau fourfolds, and things get messier. We have deformation.
I'm sorry, what is
Yeah.
A?
Sorry?
What is
A
A?
doesn't exist. A is my fantasy. So what you should do is you should think of the moduli space in this way. So you should fantasize that an A exists, but A doesn't really exist. All that exists is its tangent bundle along M. So A is some smooth ambient space modeled on this E0, but it doesn't really exist. It only exists locally, but it doesn't matter because you managed to localize everything back to M.
So
Is it like the only construction of a virtual fundamental class?
No. There's a construction using arted stacks. If that, yeah. There's more abstract constructions, but they all amount to this. They're all equivalent to this.
Yeah, so this basically says that there is a quasi-smooth enhancement of this M, and those abstract constructions, as far as I understand, just use the fancy word quasi-smooth, but it's the same idea. So
Okay.
locally being cut out by the correct amount of curves.
Yeah. Anyway, this is how you should think about virtual cycles. Yeah. So for Calabi-Yau fourfolds, things are more complicated. So the Serre duality now gives you instead a duality between x2 and its dual, an isomorphism. So actually that's a quadratic form, and that's why quadratic bundles enter into this. And now we have higher obstructions. So x3 is now dual to x1. Okay, so we can't apply Behr-Enfantecki. It looks like we're in trouble. And the point is that, you know, putting this over the moduli space and globalizing it, what this says is the obstruction theory is now three-term, but it's got this nice duality. So the bundle in the middle, E1, is an orthogonal bundle. That's essentially this globalization of this Serre duality, of this pairing here. And the zeroth and second bundle are dual to each other, and the maps are dual to each other. All right, so it's got a nice symmetry, but it's three-term. So the way you should think of that is that morally M is now described by not the zero locus of an arbitrary section of an arbitrary bundle, but of an isotropic section of an orthogonal bundle. Okay, so this is the picture. Again, A is a fantasy, it doesn't actually exist, but locally it exists. You can produce local models. And then this QSS condition says, you know, that S doesn't just take values in E, it takes values in sort of the kernel of the map from E to E dual given by pairing with S. So it's like you're taking values in a sheaf, and that's a dreadful thing to try and do intersection theory, and you don't want to be intersecting with the zero section of a sheaf. But what you can do instead is take this square root Euler class, and that's what we're going to do. Okay. So actually, this fantasy picture is globally true if you use some infinite dimensional gauge theory. But you know, for us algebraic geometers, we use the fact that it's locally true. So that's proved by these guys, whose names I don't have time to say because I'm late. Apologies to them, but J is Joyce. And there's also an orientation on this quadratic bundle by other work of Team Joyce. And as usual, we can't patch together local models. So this picture here, we could only patch together in infinite dimensions. In finite dimensions, they don't patch. But the linearization does patch, and that's enough to prove that the cone patches. So you take the graph, you make it vertical, you make it lie over the moduli space. So you're no longer using the ambient space. And that does patch. So the cone does patch. And what you end up with is an isotropic cone in a quadratic bundle. And now you can define the virtual cycle to be the intersection of that cone with the zero section in this square rooted sense. Okay, and then that has very nice properties. And what this amounts to doing is we're taking this complex, this three-term complex, and we're halving it. So we're not taking the stupid truncation, because that would obviously be a bad thing to do. would be homotopy invariant. We're halving it by losing one term and then replacing E by half of E, so using lambda. And the problem is ds doesn't really lie in lambda, and that's why we have to do so much work. And Borisov-Joyce, what they did instead was they halved it by replacing E by this real subbundle, essentially. And so they did real derived geometry, and it was awfully complicated.
Sorry,
Okay.
Richard, when you say
Yeah.
half, what do you mean?
Oh, I just mean take this T,
Yeah.
keep that, replace E by this maximal isotropic, which is half of E, and throw away this T star.
Ah.
That's what half means. So
Oh,
turn it into two terms, essentially.
Oh, nice. Yeah, I see.
And what they do, the way they halve it is they also throw away the T star and they replace E by this ER, essentially. Okay, and then we show the paper should appear very shortly that the results are the same. Okay, and then I ought to finish, so I'm going to very quickly skim through this. I'm going to say, you guys, you're K-theorists, you know very well the K-theoretic Euler class of a bundle using Cazul complexes, and you know how to localize it using a section. There's also a square root version of this in K-theory. So what you do is you take the Cazul complex, essentially, of the maximal isotropic, and then to make things symmetric, if I replace lambda by lambda dual, we tensor by this square root of the determinant of lambda. And that, up to this usual sign, is some K-theory class. And again, we have to use, we have to invert 2 to define this square root. But having done that, you get some kind of K-theoretic square root Euler class. And then you can work on the cover, produce it there, push down, and you get this K-theoretic square root Euler class whose square is indeed the usual K-theoretic Euler class. And then again, you can localize it. So I won't, there's the definition. And that gives us a K-theoretic virtual cycle. So in other words, a virtual structure sheaf on the moduli space. And here's the definition. So I ran out of time, and the two are related by a virtual Riemann-Roch theorem. There it is at the top. And we also prove a torus localization formula, which means that you can really get to grips and calculate with these virtual cycles and virtual structure sheaves when a torus acts on your Calabi-Yau fourfold, because then you can localize to fixed points and do combinatorial calculations to actually compute these virtual cycles. And lots of people have been doing that. Actually, people were doing that before we defined the cycle. They were hoping that there'd be a way of defining this cycle. So there's a whole bunch of papers which already exist doing computations of these virtual classes from before they were defined. Okay, I stop there. Sorry, I overran.
Are there questions?
You should unmute, Ezra.
Sorry, I have a question. Hello. Yeah. So when you took sort of half of the abstraction complex,
Yeah.
Is that actually the tangent complex of some Lagrangian sub scheme?
Maybe. It's not, it's certainly not an obstruction complex of the moduli space.
Mm-hmm. Mm-hmm.
Essentially,
Yeah.
because this section might not lambda in lambda. Yeah. It is, this Borisov-Joyce, you know, they define a derived structure on the moduli space using this projection of the section to the real subbundle. So in some real sense, the answer to your question is yes for Borisov-Joyce.
Mm-hmm.
For us, maybe, I don't know.
Mm. Okay, thanks.
It's a good question, yeah, I wonder.
I mean, I don't know, I can't immediately think what implications it would have, but it would sort of lift what you're doing to some.
I bet you're right, you know. I mean,
yeah,
these people who do -2 shifted symplectic geometry, you know, they express everything in terms of shifted Lagrangians and so on. And Pridham has a way of defining this virtual cycle. He can't do it in general yet, but he has a way of doing it when, you know, when you have this fantasy model that I wrote down here,
Yeah.
he has a way of defining the virtual cycle using quantization. It all sounds very familiar to what you just, similar to what you just said, but I'm not good enough with this fancy language to answer your question.
But one still has to construct the Lagrangian. I mean, you know, you're talking about what would happen if you did have the Lagrangian, but it's a more geometric question, I think, whether it's even possible to characterize it somehow.
Yeah.
Yeah. Okay, thanks.
I have an impolite question. So I think you have somehow simplified the story for us, because it looks like you just took the Kim-Lee localization business, and then you observe that the abstraction theory for your stack is what it is, and then you're just done with solving a huge enumerative geometry problem. How come?
And what do you think was dishonest about that?
So what people didn't like after the Kim-Lee work, what people didn't realize was how the abstraction theory for the stack looks like, or what people didn't know.
Well, Kim and Lee were not using, they were working with a much more general setup. They were not using anything to do with orthogonal bundles or maximal isotropics, or they were in a situation where you had an obstruction theory and not a section of the obstruction bundle, but a cosection.
So what was the hardest thing to guess for you? Like the insight?
What was the insight? Yeah, the fact that, you know, I mean, to me, the insight is Edidin-Graham's is that you can do everything you want to do by using maximal isotropics. That's the main insight. But then the question becomes, it then becomes obvious in these moduli of sheaves on Calabi-Yau fourfolds, if you've spent your life working with moduli of sheaves on Calabi-Yau manifolds like I have, it becomes obvious that the question then becomes, can I localize this Edidin-Graham class? And you can see you can localize it to the zeros of this S dual. And then how do you use the other part of the section? Well, you just have to see what geometrically is the other part of the section. How does it fit into the problem? And it just becomes obvious it's a cosection. Yeah, I don't know. Like all the mathematics, once you look at it in the correct order, it all becomes obvious. But of course, we didn't look at it in the correct order for an awful long time, so nothing was obvious.
Okay, cool. Are there more questions? Well, let's thank Richard again. Let me stop recording, then usually people ask something.